Yes. Class with me. This is 1, 2, 3. Actually, be reception. Okay. She can come in now. Can you come right about the truth? If you pick, if you camera picture, it on the truth, it was an issue. Yeah. Okay. All right. Okay. Okay. All right. Okay.
Am I? Maybe two? I can't see any. I can't see. Pen.
Yes.
But the other buttons, they are not showing me where I can take feedback.
Okay.
Yeah, I can share first attendance.
Okay.
Just need to that. You put the display on the panel of the option.
Okay. Okay. So
when I get back to the lecture, and I need to show it in full as far slideshows.
Slideshow.
I want to be sure it's not going to take me out of that.
Okay, out of this place. Okay. Okay. I did something now. Okay. Okay.
I can teach it like that.
Okay. Do I have my funny problem?
Okay. Okay, good morning, class. Hope they can hear me.
Yes.
Okay, I hope you can hear me. Let me know you can hear me. Let me have your response to know that you can hear me. The class is starting now. We had some technical issues, but we are starting. Okay, you can hear me. Great. So the first thing I'm going to do because of our time is to give you the first attendance code. So I'll quickly share the first attendance code to ensure that we are all together. The first attendance code for today is PG3F8. P for Paul, G for goal, figure 3, F for future, and 8, all in upper cases. Capital letter G, P, G, 3, F8. PG3F8. That is the code I've just given out. PG3F8. P for Paul, G for goal, 3, F for future, and 8, all in upper cases. The figures, you should take notes. PG3F8. So we go on to today's class, and we might just have to manage with the screen display because it seems there are some technical issues, and we would rather have this than have nothing. So at the last class, I was able to show you how you measure enthalpy changes, and I described to you two major ways, that is measuring enthalpy changes of combustion and enthalpy changes of reaction. And I gave you a common example of using the coffee cup calorimeter, where you can pour your substance and then take the initial temperature, then introduce a second reactant and take the final temperature. And I describe it to you that the heat lost by the solution in the course of the reaction is the heat gained by the calorimeter. So we can then use heat capacity equation to calculate the enthalpy change from there. You can have enthalpy of neutralization, for instance, and I described to you that the enthalpy of neutralization is the heat evolved when 1 mole of hydrogen ion from an acid reacts with 1 mole of OH from a base to produce 1 mole of water. So you should note 1 mole of H plus from acid, 1 mole of OH minus from base, and these two combine together to form 1 mole of water. And that is what you have in the example that I've given here. So having said that, I also went on to define the standard enthalpy of formation for you. That is the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states. So standard states are 298 Kelvin and 1 atmosphere pressure. Without wasting time, we look through the different examples that we could accommodate during the lecture. And then we talked about enthalpy of combustion. I'm just doing a recap. And I gave you this example. I think that was where we stopped. And in this example, I hope I'll be able to use the pen today. Okay, in this example, we were able to see that we can calculate the enthalpy of the reaction. And I gave you the solution using my hand apart from what is on the screen. So let's look at another example. Unfortunately, we are unable to use the pen today, but let me see if I'll be able to so today, this example 2 is very important because in this case, we have 1 mole of benzene, which is C6H6, is bound in oxygen, definitely, to give you CO2 and H2O. And we were told that 782 kilocalorie heat is evolved. I want you to pay attention to this question. The question says, calculate the enthalpy of formation of benzene in kilojoule per mole and kilocalorie per mole, given that the enthalpy of formation of CO2 and H2O are minus 294 and minus 296 kilojoule per mole respectively. You have to comment on your answer. So what do we do? How do we approach this? So we have not been told that C6H6 was reacting with water, with oxygen, but since you have been told that it was bond, you know that means you have C6H6 plus oxygen. How many moles of oxygen? Then you will have to, oh, sorry, let me put this. So this will give you CO2 and H2O. That is what to expect. So if you balance that equation without wasting time, this is what to have. If you now look at the question says that 782 kilocalorie heat was evolved. So that means that heat that was evolved implies that delta H there was negative, because we said heat is evolved. Losing of heat means that the delta H will be negative. So what then do we need to do? The delta H for this reaction, we can as well say, oh, delta H of combustion. That will not be out of place, but we are also free to say delta H of reaction. So if you convert the kilocalorie to joules, you will have minus 3.27 times 10 to power 3 kilojoules. By now, you should know some of these constants, that 1 calorie is equal to conversion of units, 4.184 joules. So once we have done that, we are doing this because the question says you should calculate the delta H of formation of benzene in kilojoule per mole and in kilocalorie per mole. So we are starting with calculation in kilojoule per mole. So we come back to say that delta H of the reaction is this, because we have to maintain the units that we want to have in the final answer. So the equation that you have always known is this, which is the summation of the delta H of formation of all the products minus summation of the delta H of all of the reactants. So coming back to this equation, our products are H2O and CO2. And we have been given the delta H of formation of CO2 and H2O. So substituting all of this value and then putting the coefficient of the reaction, we can see for the stoichiometry, we can see that that is what the answer will give us. However, the values we have. Then if we come to the reactant side, on the reactant side, we have benzene and we have oxygen. Oxygen is in its standard state, is occurring in its natural state, most stable state, so it is 0. And so we are left with delta H of formation of benzene there. So if you substitute all of these values, you will see that this is the only unknown that you are left with. And making that the subject of the formula, you can see this is the value for the delta H of formation of benzene. Having said that, the second part of the question says that you should calculate delta H of formation of benzene in kilocalorie per mole. So what we need to do is to come back and have the value converted to kilocalorie per mole, and that is what we have just done. So this is how you solve problems using this enthalpy approach, enthalpy law of reactions. And then we move on to another very important topic, and that is Hess's law of enthalpy summation. Hess's law of enthalpy summation is very crucial, and I want you to please take time to listen and listen to me very well. This is not a part of the course to joke with, because it's the main application. The slide isn't showing. I hope you can see the slides. I'm back to, it looks like the slide doesn't show when I go to slideshow.
Slideshow, okay.
It looks like they don't see it when I go to slideshow. So I went to slideshow earlier. But this will not allow me to use my finger. And it has a lot of calculations. So hold on, please. Let's check what the problem is. Hello? I want somebody to please. Oh, God, if it is the slideshow that is giving. Just give us a minute. We want to resolve the issue with the slideshow.
Hello, sir. Okay, now. It's okay. It's okay now, sir. Yes.
Okay. Hello, students. We are back. It's now showing. Thank you for telling us it's now showing. So while we are trying to stabilize, thank you, we can see it now. I want to share the second code for today, the attendance code. I will share it now. So get ready to take the attendance code and to submit it. The second attendance code is all in upper cases. U L Y S. U L Y X. That is the second attendance code. All in upper cases. U for United, another U for United, L for learning, Y for yes, and S for super. U L Y S. That is the attendance code. The second attendance code, please. U L Y S. Thank you for your response. It's now working, and we are thankful that we could do that. I hope the second attendance is taken already. U L Y S. Okay, so let's talk about Hess's law of enthalpy summation. And I need you to be fully with me, because this is, I've simplified this notes, but this is a major application of enthalpy change. So what does Hess's law of enthalpy summation say? It states that the enthalpy change for a given reaction is a constant under given conditions of temperature and pressure, and is independent of the number of steps by which the reaction occurs. So I want you to pay attention to the keywords. The enthalpy change for a given reaction is a constant, provided you are working under a given condition of temperature and pressure that you are not changing. And it is independent of the number of steps by which the reaction occurs. So what do we mean by this? How do we relate to this? You are all students of OAU. In simple arithmetic, you may say that the distance you are covering to move from one state to another state, or one place, or one location on campus to another location, the distance will vary. You may even say the amount of energy that you use is going to vary. But in terms of enthalpy change, if you want to go from any point, okay, between SUB and campus gates, for instance, okay, maybe campus gates, you know that that is a straight line. But assuming there are other routes through which you can go from SUB bus stop to campus gates, let's assume you can first of all go through road 7 and then go out and then connect with road 7. All of those things will not matter in terms of change in enthalpy. That is what we are saying. So if you have a reaction, A reacting with B, in that reaction, it can as well take a path that is so straight that it goes to C and D. So this is the initial state, this is initial, and this is final. Now, Hess's law is saying that irrespective of the path or the number of steps you have to follow to get to final state from the initial state, the enthalpy change is going to be constant, which means that if you have a straight line or a straight route or one-step process to go from initial state to final state, it's fine. But if you don't have if you have to go through some other steps, the delta H is still going to be the same for the summation of all the steps that you take to ensure that you go from initial state to final state. So if you look at this example again, reactants A and B are involved in a reaction, and C and D will be their final state, that is the product. So if you first of all go from A and B to form E and H, that may seem like a longer route because we will now go from C and H to go and form C plus D. But the total enthalpy changes involved as we move through the two steps will just be the same thing as the enthalpy change as if you are going through one step. So it means that delta H1 is going to be equal to H2, delta H2 plus delta H3. Don't forget, all of these are in standard states. So that makes the condition to be constant for all of them. So how then do we apply this? To apply this law, I have some points to help you understand it. So if you are using Hess's law to compute enthalpy changes for reactions, you need to bear in mind certain rules. Very simple rules. Number one is that if a reaction is reversed, the sign is also reversed. So in the course of taking different steps to get to the final state, if at any point in time you are reversing a reaction, then you should bear in mind that the delta H sign will change. So if it was negative before, it will change to positive. It was positive before, it will change to negative. I think you can readily relate to this based on what I taught you earlier on, that when you change, there are some states change of states that will mean that delta H can become negative of the other. Now, the second one is that the magnitude of delta H is directly proportional to the quantities of reactants and products in the reaction. I also explained this earlier on when I was giving you an example where we use chromates, and I told you if you have to reduce the stoichiometry by a factor, say 2, then you have to reduce all the stoichiometry and then delta H value as well. So that is talking about magnitude of delta H being proportional to the quantities of the reactants and products in the reaction. So if you have the coefficients in the balanced reaction multiplied by an integer, then the value of delta H will be multiplied by the same integer. And if you divide it, then you will have to divide it by that integer. So let's look at a few examples before we end the class, or close this topic out completely. So for Hess's law, these examples will help you. If you have a reaction of water in gaseous state forming water in liquid state, how do you determine the enthalpy change for this reaction? Mind you, you might be saying, oh, this is water and it's also water. I told you earlier on that the states of any substance matters in the enthalpy value, not just the sign, but the value. So for gas, water in gaseous state, delta H is minus 242. I gave that in the earlier notes. So for water in liquid state, it is minus 286. So you have to come back and apply that equation that delta H of the reaction is actually equal to delta H summation of all of this for the product minus that of the reactant. So it's the same principle that we have applied here. So for the reactants, you have H2O in gaseous state. So your reactant is this, and your product has this value. And so you're going to find that minus 44 kilojoule per mole is the enthalpy of this reaction. So this is also a reminder, like I said, I already wrote it for you. For condensation, that is what you have. But if you want to break it down into steps, it's also easy. The delta H of formation of liquid water is this value, which means that when you are forming water in liquid state, you are going to start with H2 and oxygen. If we want to have water in gaseous state, if it breaks down, it's going to give us H2 and oxygen as well. So if you look at the enthalpy for this reaction, and then you look at the enthalpy for this second reaction, they are not the same. Okay? They are not the same. This reaction is formation of liquid water, and this reaction is the decomposition or the breaking down of H2O gas. So what we have done here is also good for us because we have arranged these reactants in a way that you can cancel out some sides. Let me take you back to what I have done. If you look at this case, is the reverse of the formation of H2O. And so the sign has changed to plus 242. So the formation of H2O gas is what we know as minus 242. But then the breaking down of it is going to change the sign. So once we arrange it in that manner that we can cancel out some expressions, we can as well do the overall reaction, do the calculation. So once you do this, all you need to do is to cancel out all the intermediates. And that is what I have done here. So reversing this process turn the sign of delta H to plus. This one is left as formation of liquid water. So we can cancel out common terms which are intermediate, because assuming we want to write this reaction as overall reaction, we cannot leave the intermediate or common terms on the reactant side and on the product side. We can cancel out for step 1 and step 2. So if we had equations 1 to 2, we will see that H2 and O2 will cancel out, and then we can sum these two enthalpies. So summing them is going to leave us with minus 44 kilojoule per mole. So that is one way to apply Hess's law. It's very simple, very versatile at the same time, and very interesting once you know it. Let's look at this example. Example 2. I've given you a reaction, 3 steps for a particular reaction. This is the reaction we are focusing on. But we are saying that there are 3 steps by which this reaction can occur. And if you bear in mind the law of summation of enthalpy, that is Hess's law of summation of enthalpy, you will know that you have to put all of these together to be able to arrive at this. And how do we do that? Before we go on, you can see the delta H values for each of the steps. Step 1 is plus 90, step 2 is minus 56, and step 3 is minus 58 kilojoule. So what does this mean for us as we continue this law? We can see the solution. So I brought all of this back so that we won't have to be going back and forth. So you will just follow me as I do this. So production of N2O4 through NO and NO2 will require that we look at all the steps, ask ourselves, which one do we need to reverse? Which one do we need to multiply by a factor to ensure that we can cancel out some reactants or intermediates, as the case may be? So if you take this first one, we can see that here we have N2, and well, interestingly, we don't have N2 elsewhere, but we have oxygen here. And then we also have oxygen here. So those are the 2 places where we have oxygen. We have this, and we also have this. So going back to the question, this is the overall reaction we are looking for, which means that we actually do not need oxygen and we do not need NO in the process. What else is it that we need to cancel out? I think that would be all, because we must be left with this. We must still be having this, and then this will be our product. So it's very simple. What then do we do after examining the questions, the steps? Then we need to see which one is on the reactant side in the reaction of interest. This is the reaction of interest. On the reactant side, we have N2. So interestingly, here we have N2 on the reactant side. So that equation, we won't need to reverse it. But then we have oxygen on the product side here, and then we have N2O4 on the product side. So N2O4 is on the product side here. So we don't need to reverse that. So we essentially need to look at the ones that we need to reverse. And I think looking at this, we don't really need to reverse any of them. That's fine. The second thing we need to look at is how many moles do we need to deal with after all. So you come back and write this equation again. So let me delete all that I have written here. For us to balance this equation, we already said oxygen will remain. Because oxygen will remain, we cannot cancel out that. But we know that this will go and this will go. In the products, we have 1 mole of this. Then here we have 2 moles of NO2, which means that they will have to go. So once we write it out, for us to have 2 moles of oxygen, we cannot maintain half mole and half mole because the summation will give you 1 mole of oxygen. So we can then go ahead and multiply this step by 2. And if we multiply that step by 2, we will still need another step to be multiplied for us to have a whole number that will give us 2. So if we multiply this by 2, then we will have this new value for delta H. Because we have multiplied step 1 by 2, it's not only the coefficient of the reactions that we multiply by 2, we also multiply delta H by 2, and that is how we get 180, still positive. So from 90, we now have 180. For the second step, we are multiplying it by 2. So this will also become 112 while we introduce, we double the coefficient of the reaction. This one will be fine because we want to maintain the step. We don't need to change anything. So since we have written it out in this form, all we need to do is to sum steps 1, 2, and 3. And then once we sum steps 1, 2, and 3 for the equation of reaction, we also sum their enthalpy values. Whatever we get will give us the final answer. So, but before we can sum all the steps, some species must cancel out. And the ones that we cancel out, clearly, I told us that if this is the reaction we are looking for, we retain this. So oxygen, we go. Oxygen, we go. 2 NO here, we cancel out 2 NO here. Sorry, oxygen will not go, pardon me. We are not going to delete oxygen. We are retaining oxygen, so 1 oxygen plus 1 oxygen will give us this. Nitrogen is N2, it will remain here. But this will go. So we cancel this out. This also cancels this out. So interestingly, that is all. It's not so complicated. We are just canceling 1 intermediate. So once we had the 3 reactions together, there are 2 intermediates, sorry, NO2 and NO, pardon me. This is NO2 and this is NO. So we have cancelled out 2 intermediates, NO2 and NO. So if NO is removed and NO2 is also removed, then we are left with equation 4. So this is the equation of interest. And so if we sum 180 plus 180 with minus 112 and minus 58, and that is how the problem gets solved. So it's quite interesting, really, and I'm sure you will find it very useful. Because my time is almost up, if you can do a screenshot of this exercise, please do it and solve it on your own. It's for you to practice with, and I've given you the final answer for question 2. I want to give the attendance code, the third attendance code. Our time is fast spent. Third attendance code, VYXTG, all in upper cases. VYXTG. V for Venus, Y for youth, X for xylophone, T for telephone, G for greatness. Please take the attendance. If you are not hearing me or you are not saying it's your network, I can see that many people are saying they can see, they can hear. But whatever your challenges are, you can always go back to this lecture note online. I'll take the attendance code again. The third attendance code, VYXTG. V for Venus, Y for youth, X for xylophone, T for telegram, G for greatness. VYXTG. VYXTG. X, not S. V for Venus. V for Venus, Y for youth, X for xylophone, T for telegram, G for greatness. VYXTG. V for Venus, or V for velocity. Y for youth. V for velocity. V for velocity. Y for you. X for xylophone. T for telegram. G for greatness. So if you have any question, I will quickly take it and we will be done in the next few minutes. Let me see if you have any question as we look at. Please take your time to look at the practice question that I've posted there. You will find it very helpful, and I'm going to continue the class from there on Monday, God willing. You can also look at this example too. I gave it earlier on, but I've typed it because some of you complained that you could not see it. So it's not a new example. So we are stopping at Hess's law, and in the next class, we'll continue with Born-Haber cycle. So please, if you have any question, I'm still here to take your question. Is anyone having attendance issue? Problem with attendance page? They said no. So please check your network. The attendance is going through, and the third code is VYXTG. So please check. I said VY, V for Venus, Y for youth. I didn't say VY. V for Venus. V for Venus, Y for youth, X for xylophone, T for telegram, G for greatness. VYXTG. If you are not hearing me, it's probably that your network is bad at your end. V for Venus was what I said. And I made it clear. I've called it like 5 times already. So it seems there is no question. And we expect you to submit your attendance. And please take time to go through the practice question that I gave you. I think somebody is asking about the test. Your test date will be announced shortly. If you have not received any message, please be on the lookout. Thank you and have a great day. I will see you on Monday.
Yeah. Okay.
They usually left there because of their attendance issue.
Okay.
So some of them, they are complaining. I guess it's their network.
Okay, it's their network. It's not from. It's not
Just
from
let them
here.
switch to 1 minute. Before they are shut out. Okay,
you are welcome, ma. Yes, ma. Madam. Yes, ma. I need to, ma. Welcome. Ìjẹ́jú kò sá. I said, Drew, maybe it's time I'm actually there. It's time.